Up here. Right. So a couple things. The exams are not graded yet, so we'll have to go till Tuesday again. They'll probably be ready at, as soon as we dismiss. That's the way it goes. It's kind of hard to predict. Sometimes they have a huge backlog to grade. Sometimes I've turned them in there and had them come back 2 hours later. It just depends, and you can't predict it. So anyway, so probably Tuesday we'll have printouts for you. By the way, I promised you a blurb file for each test form for each midterm. You guys ready? Yeah. No, don't look back there. You. Are you ready? You guys are talking over there. Not you in the green shirt, the people next to you. Yeah, you two guys. Okay, when I'm talking, we're wasting time. All right, so I'll try to produce and PDF those blurb sheets for you so that you can use it as a study, kind of like a mini study guide for the final, almost. So, and so you'll get your printout Tuesday, and so you'll have two printouts. By the way, another thing I want to mention, it's not in the notes for today, but most of you in here now have 2 exam scores. Now, it's possible that if you take midterm 4 and then have 3 exam scores, one of the 2 scores on the books now will get dropped. Okay? Now, after exam 4, we either keep exam 4 and drop exam X or exam 3, or drop exam 4 and keep exam X and exam 3. So the main thing is, right now, we have 2 exam scores, so we can start thinking about how to estimate your semester grade. Now, we got about another month and change before we get to the end of the semester, but we're in the position now where we got enough dineros other than the final. I mean, we don't have the final yet, but so there's 2 50-point midterms on the books now. And you may have noticed I put 2 new lines in the grades page. I'm going to update everybody's clicking dineros, the clicking answers, and the clicking correct as of today. I'll probably do that this weekend. So you'll have numbers there, and you'll be able to estimate your participation pointage, right? So that's something out of 45. And we did that a couple lectures ago. I showed you how to work that out, right? You'll be able to, as soon as I get those data in and your exam 3 data in, you'll be able to start checking out your grade status going into the last month and into the last week of the final, the last week of the semester, i.e. final exam week. So that's on the horizon, and just to remind you, do not discuss your grades in discussions, right? That is, if I spot it, I'll delete it, all right? But you can talk to me in messaging about your grades and stuff, if you have any concerns and you're worried and stuff, which, it's normal. This time of the semester, people are a little nervous about their grades and stuff like that. But don't do it in discussions, because that's not private. Do it in messaging, and that is considered private and secure. By the way, somebody left some glasses up here. I don't know whose they are. They're looking kind of stylish, but I'm tempted to borrow them permanently. But anyways, I heard a rumor that it was somebody in this class. If it's you, you don't have to come up now. If you're embarrassed, you come up later and get them. I'll just put them down here so they're out of the way. Okay. Now, another thing I want to review with you is there's a Nights Under the Stars session, not on a Wednesday night, but on Sunday night. So it's a special edition devoted to lunar observations. And it's over at the CFE Arena, Knights Plaza, Sunday evening. And right now it's still purple, but if it goes green sometime on Sunday, get your boop over there. And remember, the procedure is get the handout, do your observations, record them on the handout, and then give the handout to the guys that are in UCF Astronomical Society. Don't bring them to class. That's no good. It's got to be handed it to them. And then they'll get it to me. And I've got a stack like about this thick from you guys that went to the one 2 weeks ago, whatever it was. Right? They just got that to me. So that's how that works. Anyways, I'm actually going to try to go to this one on Sunday night. So if you see me there, you can give me the business or whatnot. And hopefully it will be, you know what? That is not, unless they can get the street lights turned off, we're not going to be able to see many stars because it's blazing with light there at that night by the arena. So, but we should be able to see the moon pretty nicely. That you don't have to worry about. Okay. Any other questions about any of that stuff? Let's keep going. We're going to dip into chapter 15 and then dip forward into chapter 16 today to talk about nuclear reactions. And then we're going to dip back into chapter 15 on Monday, or excuse me, on Tuesday. So, and you're going to have a big homework this weekend, reading chapter 15, reading chapter 16. You know, I like this book a lot. And I hope you guys are finding it helpful, especially helpful for your wallet, because it's free, unlike these $150 books that most classes have to use. Anyways, so there'll be a big homework, chapter 15, chapter 16, but we're going to be dipping back and forth a little bit. So just mentally think of those two chapters as one big chapter, and we're going to be roaming around in that. This is a pull quote from chapter 15. The sun's core is extremely dense and hot, I might add, and it is the source of all the energy. Inside the core, nuclear energy is being released. Now, we're going to be talking about that today. We're going to talk a little bit about the structure of the sun, the core, the atmosphere, and so forth, and we're going to talk about Einstein's theory of relativity, E equals mc squared, that big famous equation. Now, when we say that the sun forms, natural formation of a fusion reactor, that's basically the process where the sun, it forms like H.L. Tori here, it forms like from a big swirl of dust. And go ahead and make a note of this term. It organizes itself gravitationally. The star organizes itself gravitationally. It is a self-gravitating system. In other words, it's gravity that brings it together and eventually smushes it down to density and heatness where the nuclear reactions start to light off. And they won't start at a low temperature, like in our room, of course, it's got to be ultra hot, many millions of degrees of temperature. But it's, so when I talk about natural formation, I'm saying, all right, this is a star. This one's already, The bright star HL Tauri in the middle of this, it's probably pretty young. I should look that up. What's the age of HL Tauri? But it's still pretty young, and you know why I know it's young? Because the planets are still sweeping the rest of that star system. You can see the lanes there. We talked about that last week. So HL Tauri is an example of a star that is nuclear reacting, having condensed itself from a bigger cloud, a bigger disk, gravitationally. And that's the process that we're going to talk about. Here's a picture of the sun structure. It's very common. It's a nice one. This is from your textbook. The core, the innermost region is called the core, and that, my wonderful students, is where the nuclear reactions are cooking. And go ahead and make a side note. In our star, it is mostly hydrogen nuclei fusing together to form helium nuclei. All right, so a hydrogen nucleus is just a proton. So that's really the simplest nucleus in the universe. And by the way, some of you were saying, hey, Dr. B, why does it say most isotopes or most elements? And the reason I said that is because there is one element that doesn't have any neutrons in it, and that's hydrogen. Question, Chanel. What did I say? Yeah, our star is like many stars. It's hydrogen nuclei, protons, 4 of them, fusing and nuclear reacting into a helium nucleus. And a helium-4 nucleus is 2 protons and 2 neutrons bound together. And in that process, it's kind of weird, Chanel, but a little bit of mass goes missing. And that missing mass, so you take the mass of 4 protons, and then you compare it to the mass of a helium-4 nucleus, and the helium-4 nucleus is a little bit lighter, not much, but they can measure it, and that missing mass goes into E equals mc squared and turns it into energy. That's how nuclear reactions work. Anyways, all that's cooking down the core. Now, a bigger star, like a red giant star, you might have carbon, nitrogen, and oxygen cooking down there, along with the hydrogen and the helium. And we can have nuclear reactions all the way up to iron. Iron is where the nuclear fusion stops. You don't get much energy if you go past iron.
How does helium come from hydrogen if hydrogen doesn't have neutrons?
We'll talk about it next week. It's the nuclear reaction. And it cooks like a chemical reaction, you take 2 elements, you combine them in the right way, and you have a new compound, molecular compound. Like hydrogen gas and oxygen gas. You combine them under the right conditions, you get H2O. All right? Completely different, chemical compound. The water of life. Hydrogen is rocket fuel, and oxygen is also an oxidant. You need oxygen to make anything burn. So those 2 things together, or separately, are like almost weapons of mass destruction, right? But H2O together, the same stuff, but put together in a chemical reaction, H2O, the water of life. And the same thing with nuclear reactions. You're putting two different nuclei together, or 2 of the same kind, 2 hydrogens together, and you fuse them into something new, a new nucleus. So it's not a chemical reaction, but a nuclear reaction. And I'll show you how it cooks out. It's kind of a chain reaction. And at the end of it, you get some helium-4 nuclei. The outermost part is called the corona, and that's the part that you see in a total eclipse of the sun. The moon moves in front, just like we saw at the beginning of the semester. I think a bunch of you saw it. And in between those 2, the outermost corona and the innermost core, there's a huge number of physics principles and concepts at work. For one thing, and you can look at it in the diagram from chapter 15, convection. They'll talk about convection. You know, just like water boiling on the stove, it kind of rolls. You know, you get a rolling boil, that's convection. And we can actually see convection cells on the surface of the SUN. They're gigantic. But you know, a big convection cell here in Orlando, outside the kitchen, but much bigger, thunderstorms. You know, those are convection cells. They're very, very big compared to us. Compared to the sun, they're nothing great. Another physical process, radiation. There's a whole zone of the sun that's called the radiation zone. Other stuff that's happening is enormous magnetic field strength. There's some really big magnetic fields that form, break apart, reform, and in that process of forming and breaking and reforming, breaking again and reforming, it's all connected, Shaylin, to the convection that's going on, and it heats up the corona, we think, to enormous temperatures. But to get to the bottom of all these processes, the thing that we want to talk about now, and we're dipping over to chapter 16 now, is energy, specifically nuclear energy. Now let me give you a short blurb about what energy is. So if you haven't had physical science 1121 or physics 2048 or a high school physics class, you might need to learn a little bit. So let's talk about energy and luminosity in the metric system. So this is kind of pre-reading concepts, and actually they have a little bit about kinetic energy. The metric system unit of mass is kilogram. The metric system unit of time is the second. The metric system unit of distance is the meter and the centimeter. The metric system unit of energy is the joule. And the 1 joule of energy is effectively the kinetic energy of a 2 kilogram object moving at 1 meter per second. All right, and that's because the kinetic energy formula, you may remember this if you've ever had a physics or a physical science class, 1/2 mv squared. Right? So it's a bunch of kilograms, and then you square the speed, whatever the speedometer rating is, and then you multiply that by the mass, and then you multiply by 1/2, and that's the kinetic energy. Right? So think of this as a 2-liter bottle of Pepsi. Okay, so 2 liters, it's about 2 kilograms, right? And it's moving at 1 meter per second, right? Now, as a side note, you can jot this down in your notes. 1 meter per second is approximately 2.24 miles per hour. So a 2 kilogram, a 2-liter bottle of Pepsi moving at about 2.2 something miles per hour. All right, that's a joule. And it's a derived unit. It is not something that we have an inherent energy scale for. You know, we can't go to some museum in Paris and look at the international joule. Now, we could do that for a gram and a meter, but we can't do it for a joule. So we say it's a derived unit. It's based on this idea of kinetic energy. Now, luminosity is rated in watts. And 1 watt is 1 joule per second. Now, if you pay your energy bill at your apartment or your home, you know that they charge you Progress, or I should say Duke Energy, Orlando Utilities Commission, et cetera, they charge you for every kilowatt hour that you use. Okay, a kilowatt hour is 1,000 watts times 3,600 seconds. So it's a lot of joules. All right, and they charge you a dime for every kilowatt hour. 8 cents, 10, depending on what your billing rate is. Okay, so watts. So for an incandescent light bulb, standard light bulb, 60 watts, Yeah, that means it's burning 60 watts, or it's actually using 60 joules every second that the light is on, right? And just a side note to you, things like incandescent bulbs are really inefficient. That's why they're trying to do away with them. They're nice for some reasons, but they waste a lot of energy just getting hot. Hair dryers, we're going to talk about them in a minute. A hair dryer has a really big wattage rating, 1,000 or more. And a lot of that, and they don't do much, they dry your hair. It's not like they're great shakes at doing things. Because heating, most of that wattage rating goes into heating. A little bit for the fan, but most of it for the heating elements. A toaster, same thing. An electric toaster, that doesn't even have a fan. It has a spring, but you operate that. And it has the heating elements. They get red hot. They they toast your toast. But it's really inefficient. It's a very inefficient. That's why people like these LED lights that are coming out.
Yeah.
They're more expensive, but in the long run, they'll last longer and they use less energy. To do 60 watts worth of lighting incandescent, you need like a few watts for LEDs. Now here's the wattage rating of the SUN. 3.8 times 10 to the 26 watts. And oh my goodness, that's a lot of watts. It's a thermal light source. I mean, it's incandescent. You can think of it that way. You're not seeing the light that you see from the sun is not the light that you would see if you were looking at the naked core of the sun as it undergoes thermonuclear reactions. Okay, that light is produced by nuclear reactions, but by the time it gets to the surface, after taking a long time, bouncing around inside the radiation zone and then through the convection zone and stuff like that, it's completely thermalized and becomes an incandescent light source. Now, I want you to jot down the sun's wattage rating. We're going to use it in just a minute because we're going to use Einstein's equation and work out how many grams or kilograms of mass has to go through E equals mc squared to get this many joules per second. We're going to figure that out. I'm going to work it through you step by step. We'll just work it together, 50-50. All right? And we'll just go. And the other thing that we're going to need is the solar constant. All right? Now, remember the solar constant. We talked about that. That's the amount of solar radiant energy, so sunlight, so all the visible colors, infrared, ultraviolet, and even a little X-rays in there. Not too much. All that's considered part of the solar constant. And it's about 1,367 watts for every square meter. So this lectern up here in front, the front of this lectern is about 2 square meters. The first half is about 1 square meter. Second half over here on the right is 1 square meter. So every square meter catches 1,367 watts. So jot that down in your notes. And remember, in Mars, the sunlight, same sun, but you're further away, so all the energy from the sun that leaves the surface is now spread out even further, and so the solar constant, so to speak, for Mars is a little bit less, and we talked about that a couple weeks ago as well. Now, I want to go through a couple other examples of energy so that you have some terrestrial examples from everyday life of the energy scales inherent in moving objects. So these are kinetic energy calculations. First of all, bumblebee, a Camaro. I wish I had one. Dude, like an Iron Man suit and a bumblebee Camaro, would that be? But no, you can't get Can't get an Iron Man suit. Anyway, so in 2016, the 2016 Camaro, when it came out, they put it through the quarter-mile test, and it got up to 115 miles per hour in 12 seconds in a quarter mile. You know, it's flat out. All right. Now, that kinetic energy, you work it all out. You know, you have to, I didn't list the mass of the Camaro, but I looked it up, and I worked it out in the metric system, 2.2 million joules. All right, so go ahead and jot that down. And jot down its speed in 12 seconds and stuff. We're going to use that in a minute. Another way to express that is 2.2 megajoules, capital M being the symbol for mega, meaning million. All right, so it's a little more compact notation. All right, now this tank down here, the M1A1 Abrams, a mighty war-fighting machine. I wish I could have one of these babies, especially when I'm trying to drive down University after class, 3, 4 in the afternoon, and all those maniacs out there. If only I could have, like, I don't even need one of these. If they would just let me put anti-tank rockets on my car and just, take out some of these maniacs out there. Anyway, so one of the regular high energy rounds from an Abrams, about 12 megajoules. I looked this one up. You can look up all these things. They have different kinds of rounds, high explosive, penetrating uranium, depleted uranium slugs and stuff. So that's a pretty good one. And the M1A1 Abrams can develop some pretty high speed. I mean, you may have a car that could get beat out by an M1A1 Abrams. I mean, if you have a beater that doesn't go more than 50, which I'm not looking at anybody, but sometimes college students don't have the best cars, but the Abrams can go pretty fast, and it's 50 miles an hour in one of those babies. That's a lot of kinetic energy. The Navy has a rail gun that they're developing, and actually I don't know if it's in service yet, but it should be in service. Hypervelocity projectile, basically a piece of metal, and they get it up to 32 megajoules of kinetic energy. And then if they aim it at the right thing, they could take it out. Just to knock, it's just like a bullet. A bullet is a chunk of metal that you get up to high kinetic energy. By the way, that's another thing you can jot down in your notes of everyday things. Raise your hand if you are a person that you hunt, you have your own deer hunting rifle and stuff, and you reload your own rounds. Anybody in here reload with their own rounds? Okay, a couple. One of the things that you have to consider and actually, even if you just buy your own ammunition, a lot of times you'll see printed the kinetic energy of the round. And if you're trying to reload or make your own custom loads, you want to calculate the kinetic energy of the slug. It's basically just like what the Navy's got. They just got a big slug, and they don't do it with gunpowder. They do it with, they have cannons, in these battleships and stuff that use gunpowder and whatnot. But the rail gun is electromagnetic, not gunpowder. Anyway, so those are some typical everyday kinetic energies. Now, the Camaro, the power rating. Well, we got a kinetic energy, 2.2 megajoules, and it's developed. And you hit the gas flat out in 12 seconds over a quarter mile. Right, so that means you can do an average power. Right? You would call this a luminosity, but you would call it a power because it's the joules per second on average for the Camaro. So you would say it's 176, 2.2 megajoules divided by 12. So type in 2.2 and then EE6, that's 2.2 million, then divide that by 12, and it comes up with 160 or 176,000. So that'd be 176,000 watts or 176 kilowatts. All right? Now go ahead and jot that down. And the reason is, you're not going to have to do these calculations on the test or anything, but I do want you to have some everyday examples to compare with. Now, this one's kind of shaky because you say to yourself, okay, Dr. B, Bumblebee, 176 kilowatts, big deal. All right, let's compare to a hairdryer. Hairdryer is about, you can go to the store down at Walmart or Kmart or something and buy a hairdryer that has a rating of 1,750 watts. You look it up. Look it up on the internets. And that's 1.75 kilowatts. All right. So this is another example where your hairdryer is 1% power of what the Camaro's putting out. But the Camaro is a gigantic piece of machinery, right? Most of that energy is going into motion. But for the hairdryer, most of the energy is going into heating up those heating elements. It's very inefficient. So you don't get much motion. I mean, you got a little fan in there, right? But that fan is zip-zap compared to a Camaro for motion. Most of that energy is going into heat elements, so it's kind of inefficient. But anyway, so that's one way you can rate things, is in terms of their energy or their power. And when we're talking about stars, we don't call it the power, we call it the luminosity. But it's measured in watts. And there's other ways to rate the luminosity, but that's the most common sense one. Now, another thing I want to go through with you is the temperature scale. And in the metric system, we have a special one called the Kelvin temperature scale. And it's really important. It's the one that we're going to use in this class. Now, if you listen to the Weather Channel, they're going to talk about Celsius and Fahrenheit a lot. All right, and Fahrenheit and Celsius, we're going to talk about Celsius a little bit in this class, but not Fahrenheit very much. But anyways, other than today, Fahrenheit, it's 32 degrees. Let me get my cursor over here. There we go. 32 degrees here for freezing point of water, 212 degrees for the boiling point of water. Notice that that's 180 degrees. That is not an accident. Professor von Fahrenheit designed it that way. And then the 0 point of Fahrenheit is down here below freezing. All right. So anyway, so here's what Professor von Fahrenheit figured out. Then the metric system is not based on 180 degrees and 212 and everything. It's based on 10, 100, 1,000, powers of 10. So the metric system is based on 100 degrees Celsius for the boiling point of water and 0 degrees Celsius for the freezing point. And so the 0 point, and now notice here, make a side note to yourself, the 0 point of Fahrenheit corresponds to minus 18 Celsius. Right? So where you put your 0 point for your temperature scale, that's up to you. Professor von Fahrenheit put it over here, and the metric system guys put it up there a little bit higher, right at the freezing point. Now, 0 is the freezing point for some kind of if I recall correctly, a salt water solution with rock salt dissolved in it or something like that, and that's why he used that for a 0 point. But regular water is 32 Fahrenheit. Anyway, so the side note to you about these two temperature scales is you can put the 0 point anywhere you want. And you can choose the size of your degrees of separation. Okay? So the metric system guys said, all right, we're going to go boiling water and freezing water, and we're going to choose our degree size so there's 100 Celsius degrees in between there. Professor von Fahrenheit, he said, well, I'd like to have 180 degrees between freezing water and boiling water. Okay, so, but separate decisions. So you can put the 0 wherever you want, and you can choose the degree sizes that you want. Let me ask you a little mental IQ test question here. See if I can get your brains. Thinking. I know it's going to hurt. Question. Which scale has larger degrees, Fahrenheit or Celsius? Celsius? Fahrenheit. Because it's 212, right? Or Celsius? What is it? So what is it? Fahrenheit or... Come on. Fahrenheit? Wrong. It's who voted for Celsius? Yeah. It's Celsius because, and here's how you think about it. Celsius has bigger degrees because you only need 100 of them between boiling and melting. But for Fahrenheit, you need 180. Right? So that's, now, the Kelvin scale is considered a metric temperature scale, but the 0 point is completely different. It uses Celsius-sized degrees. Okay, so there's still 100 kelvins between freezing and melting water, or excuse me, freezing and boiling water. But the 0 is not the freezing point of water, right? That's the Celsius scale. Celsius is oriented to water. The Kelvin scale is oriented theoretically to the molecular motion of your material. And, you know, because the hotter things are, the faster they zip around. You know, like if we heated up the air in this room, you know, by 100 Fahrenheit degrees, and if you could see the molecules, they'd be going a lot faster on average. All right. So another way to think of the 0 point of the Kelvin scale is it is the point at which no heat engine can produce useful work. There's no way to, at some point, the molecules are going to be so slowed down that you'll not be able to extract any more work. You know, any kind of a heat engine, like a steam locomotive. You pour on the coal, you pour on the wood, or whatever, you heat up the water, steam drives the pistons and the turbines, and your locomotive goes down the railroad tracks. That's a heat engine. It's based on heating up steam and making the steam do some work for you. So what we're saying here is there's a temperature called absolute 0 from which you can extract 0 useful work. All right, and that's what the absolute 0 is. But notice there's still 100 kelvins between ice and steam. All right, so that's good. It's still a metric system scale. And this is the Kelvin scale that we're going to talk about in astrophysics. So when we talk about the temperature of a black hole, the temperature of the surface of a star, the temperature of a nebula, a big blob of gas, the temperature of A, B, C through Z, we're going to talk Kelvin scale. The only time you're going to talk about Celsius or Fahrenheit is if you're talking about an atmosphere, maybe. Right? Another thing that let me pause for questions. Yes, go ahead.
So molecular motion is cool when you stop it, so there's still atomic motion.
That's right. In the quantum, and thank you for bringing that up. In the quantum sense, absolute 0 is not absolute stillness. Because the particle, the quantum interpretation of particles is that a particle is a wave, and the wave is still waving. It has a mass, it has an energy, therefore it has a wavelength, and the wave is still, the quantum mechanical wave is still waving. So that thing's still oscillating, but you still, theoretically, can extract no useful work from it with a heat engine. It won't, if you're a little bit hotter than that, yeah, you can get a little bit of heat out, a little bit of work out, but not from 0. So yeah, quantum mechanically, nothing's actually at rest. Everything's still fluxing, I guess. Now, speaking of flux, let's talk about the international expert, Roy G. Biv, famous scientist. Yeah, Roy G. Biv. He's a real guy. This is his yearbook photo from 1982. What are you talking about? And he comes from a long line, the Biv family. And all of his great-great-grandcestors in descending line have all been named Roy G. Biv. And it's really, really cool. For hundreds of years, centuries, the Biv family is honored because the letters of his name are the exact order of the visible colors of visible light: red, orange, yellow, green, blue, indigo, and violet. Right. So it's amazing that all the way back through the misty dawn of time, the Roy G. Biv family knew what to call themselves. Anyway, so Roy G. Biv. So whenever I talk about Roy G. Biv, it's an acronym. Okay, I just gave it a fancy story, but it's an acronym for the order of colors. Yes, there's not really a guy named Roy G. Biv, although his yearbook photo there. I don't know who did that. Some guy, some wiseacre did that photo. Anyways, Roy G. Biv. So whenever I talk about Roy G. Biv, I'm talking about visible light. When I'm talking about visible light, think Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. All right? And I was told by students, art students in the first lecture, that they can distinguish between blue and indigo. And I, however, I'm going to have to study up on how to distinguish between blue and indigo. Raise your hand if you know the difference. Wait a minute. If you can distinguish visually between blue and indigo. Oh, a bunch of you. See, you got the drop on me this time. There's a question over here somewhere. Yeah.
Why are there so many variants of the blue versus red or like yellow?
Why are there so many variants of what?
Like the blue group, why is there blue, indigo, violet, but only like red instead of orange, and then like a green? Why are there more?
Yeah, why is, so you're asking blue and indigo and violet are really close, and red and orange and yellow are not very close. I agree. And I don't know why. It's because the English language just has those color names. And that's all. I mean, some languages, I'm sure they have a zillion color names compared to English. So, so in countries that don't speak English but do have that language, there'd be probably some other famous scientific family with just the right name. So, anyways, here's some more things. When we're talking about colors, the color of light, actually, you can consider ultraviolet a color. We can't see it, but we can measure it. We have ultraviolet detectors. Your skin can feel it because that's what gives you sunburn. Ultraviolet. Now, this is a false color ultraviolet picture of the sun, and jot down the wavelength here. The wavelength is 304 angstroms. And an angstrom is 1/10,000,000,000th of a meter. Right? So the wavelength, it's pretty small. So this is a really tight wavelength, 304 angstroms. And we know that thermodynamically speaking, that light of this wavelength corresponds to a plasma and this is now in the sun's atmosphere, a plasma that's somewhere between 60,000 Kelvin and 80,000 Kelvin. Oh, by the way, room temperature is about 290, 300 Kelvin. Your body temperature, I don't know what it is, 300 maybe, Kelvin. Infrared light, you put out, You may wonder, why do night vision goggles work to detect humans and other things? Well, especially, like out in the desert or something, which cools off really cool at night, humans are always at 98.6. So we put out a lot of infrared just because of our temperature. And stars as well. If you have a cool star, the surface fairly cool anyways, it'll put out a lot of infrared and not much Roy G. Biv. So anyway, so our sun has got a really complicated atmosphere, and this layer of the atmosphere, it's pretty low, close to the surface, about 60,000 to 80,000. Now here's another layer, 171 angstroms. This is another false color. This is from the SOHO satellite that makes these observations several times per day. About 1 million Kelvin at 171 angstroms. All right? And so we look at this, we compare pictures, okay, 60,000, here's a million, so that reveals structure, thermal structure, physical structure. Question?
So these atmospheres are very, very thin.
They're sparse, but they're large. In fact, this one's getting larger. Here's the next one. False color ultraviolet, 195 angstroms. You can see this one extends further out.
Okay, so this is like the different atmospheres of the sun?
This is one of our SOHO space telescope looking at the sun with a filter that filters out everything except this wavelength. And we know thermodynamically that means that part of the atmosphere that's bright green or even white is at approximately 1.5 million Kelvin. But if we get a lot, see now look at the picture, Desiree, look at the picture, and everybody look at these two pictures. 1 million, 1.5, see how it changes? Let me go back to 1 million. Look, come on, look up here. Look up here, come on. All right, good. Oh, that's 2 million. I went the wrong way. Look at the difference in the structures. See that? Slightly different. These are all taken the same day, roughly the same time, but using different filters of wavelength, yeah. And so this one's 195, and this last one here, 284 angstroms. And notice how far out this one's, now you're talking about the corona. And in fact, look at this. This is what you would call a coronal hole. Not much stuff happening up there, not much ultraviolet light coming from that part. It's dark. The yellowish part, false color yellow, is bright at this wavelength. All right, so there's a lot to learn just by looking at this stuff. And scientists study this stuff. I got to tell you, my area of research is general relativity, Einstein's theory of relativity in curved space-time, quantum mechanics in curved space-time, quantum field theory, curved space-time, and it's extremely difficult. But this, magnetohydrodynamics of the sun, is one of the few areas of physics that's even harder than what I have been doing. So it's extremely difficult. But guys are studying this all the time. Question?
Do those really bright places stay in the same spot always? Or do they move? Because they look like hurricanes.
Do they stay in the same places all the time?
Yeah, or do hurricanes?
The answer to that is No. And that, my wonderful student, is why guys like to study it. Why is one area of the sun's atmosphere bright in 284 angstroms today, and then 12 hours from now it's dimmed out, and 12 hours from now this coronal hole might seal up. Why is that? Well, we want to know. And so the answer is yes, it's dynamic. These are snapshots. These are not films, but they do have, if you go to the Soho website, I'll try to put a link to it in the homework assignment. You can see all kinds of videos and stuff. It's a lot of cool videos, actually. So here's another nice image. This one's a black and white, false color, this is visible, 67. Oh no, this is visible, 67, 68 angstroms, kind of reddish. And this one's optimized to show the polarity of the magnetic field. The sunspots that are visible on the sun are always associated with magnetic field. A magnetic field, kind of like a horseshoe magnet. You know, the north end of the magnetic field loops up into the atmosphere and then loops back down and becomes the south pole of the magnet. And so that's the circulation of the magnetic field lines, or vice versa. And this particular flavor of reddish light, 67, 68, allows, if you look at it carefully, you'll see like over here on the far right, look at that, there's a white and a black right next to each other. That's a sunspot. The white is the field lines coming out, and the black is the magnetic field lines coming back in. They're looping around. And this is not a very active sun, but there's some sunspots on there. And this picture is March 4th, 2015, which is when I bagged this picture. And you can go to the Soho website and look at them today, today's image.
If that's like the false color, what's the actual color?
Red.
Red.
Yeah, it's reddish. 6700. The H alpha is 6560. So this is a little bit redder than H alpha. All right, so that's just different colors and wavelengths and stuff. Now let's talk about gravity and fusion. Clickers, please. Have your clickers on. And go ahead and start the question. Turn your clicker to option DD if you haven't already. Go ahead and close that. All right. And here's your question. What happens when you rub your hands together? What? Roy G. Biv. Leave Brittany alone. What? All right. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, good. 0. Click. Yeah, most of you got that one right. Your hands warm up. And basically that rubbing together is what causes heat to be produced when something gets compressed. All right? And actually, I can't believe it. Somebody voted for three people voted for B. What? 2 people voted for D and 1 voted for Roy G. Biv is my secret weapon. Okay. Anyways, a few of you voted for C, and actually that is not correct. Now here's how you can, if you voted for C, I want you to jot down. You could rub your hands together and emit visible light. But they would have to be really, really hot. Now you know stuff that emits Roy G. Biv light when it gets hot. Like the stove element on your stove, it gets red hot. Now you can't do that by rubbing your hands together. Thank God for that. Right? So all you can do is get hot. So emitting Roy G. Biv light is, maybe something else, but not your hands. All right, question?
An interesting fact, the crane, or not the shrimp, mantis shrimp, has a punch so fast underwater, it emits light. Now, I'm not
A
sure.
shrimp that moves it punches forward, and it's so fast it emits light. Yeah, and what that does, it's heating up the water it's to incandescence. So it's kind of cool. All right, next question. Which object heats up more? Next question. Good, start it. Yeah, good. From gravitational compression. Look at that traffic jam. I think it's in China, like Shanghai or something like that. Can you imagine being stuck in that? Even University Boulevard at 3 in the afternoon is not that bad. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, now, can you show this one? Yeah, over there. Switch to desktop or to computer. Okay, now on this one, there's a little bit of controversy there. So let's talk about this. Okay, switch back to regular one. The correct answer is large mass. Now here's why this is true. Remember when we talked about Saturn and Jupiter, and we said that the metallic layer, the metallic hydrogen layer in Saturn was deeper because of the pillows. Remember the pillows analogy? The more pillows, the more compressed it gets. It's the same thing here. So when you have a large object, it's going to heat up more. In fact, go ahead and make a note to yourself, attached to this question. If something heats up enough through gravitational compression, it will start some nuclear reactions, right? And this is how a star is born. A star is born when those nuclear reactions start to cook in the core, right? And so heating is significant from gravitational compression, but stars are not luminous at this level in Roy G. Biv and ultraviolet and infrared. They're not luminous because of gravitational compression. And the reason for that is gravity is very weak. It's an infinite range force, but it's too weak to produce that much light. Question in the back. Completely different. Those form in a completely different way. They don't form by gravitational accretion. They form in a supernova detonation, we think. So, all right. So we now know that the reason that stars are so bright, like the sun, is because of the nuclear reactions in the core. Gravitational energy is nice to heat things up, and hopefully it's big enough to get up to several million Kelvin, because when it does, you'll start the nuclear reactions. Now let's talk about nuclear reactions. Here's the equation that's famous around the world, probably the most famous equation there is, E equals mc squared. And this equation is basically saying that matter, symbolized by m, the number for its mass, how many kilograms or grams, matter has energy just because of it existing. Or another way to say it is matter and energy, they're not equivalent, but they can be converted from one to the other. Right now, we've been able to do that in the lab. Nuclear reactions are a form of converting. You'll go ahead and make a note of this. A nuclear reaction converts M into E. All right, so the little bit of missing mass after you get your helium nucleus formed, that missing mass is converted into E by this equation. All right, so this is the master equation for nuclear reactions. And they figured out in about 10 years after Einstein came up with this, he came up with it in 1905. About 10 years later, they figured, you know what? Maybe nuclear reactions, maybe we can convert mass to energy in nuclear reactions. And of course, that was true. So let's think about how much sun, or how much hydrogen the sun burns per second. Right? Now we know the luminosity, this is a chain of logic here, so jot it down carefully. First thing we know, the solar constant, 1,367 watts per square meter. All right? Now what that means is that and that's just per meter out here at 1 astronomical unit away from the sun. Now, if you think of the entire sun blazing energy at that level all the way out to a sphere, the same distance that we are, okay, and then you do all your math, and you use the formula for the surface of a sphere. Who knows the formula for the surface of a sphere? Raise your hand if you know it. Raise your hand if you know it. Raise your hand if you know the surface area of a sphere. The formula for the surface area of a sphere. What is it? Do you remember? What is it? You don't remember? What is it?
4/3 pi r.
No, that's the volume. 4/3 pi r to the third is the volume. The surface area, 4 pi times r squared. Yeah. 4 pi times r squared. All right, so you do that for r being 1 astronomical unit. It's a bunch of meters. And you square it, and then multiply by 4 pi, and then multiply by 1,367. And here's how many watts total that the sun puts out in all directions. Okay, so, just a little fraction of the sun's energy is actually aimed at Earth. And so every square meter catches 1,367 watts. And Earth's got a bunch of square meters facing the sun at any one time, the sunny side of the Earth. All right? But the actual amount that it sends out in all directions is 3.85 times 10 to the 26 watts, as we've already mentioned. All right? So this is the approximate luminosity of the sun. Now, all of that is produced because of the nuclear reactions in the core. And so we're going to use E equals mc squared, and we're going to do some calculations here. I want you to take very careful notes so that you know the numbers that we're going to talk about. Now, you're not going to have to do these calculations again on a test, so don't worry about that. But do try to follow it. Here's the fraction of mass that's converted every second. And we're going to calculate this in just a second. 4.28 times 10 to the 9 kilograms per second. That's 4.28 billion kilograms per second. 4.28 million metric tons per second. Now that's a lot on the human scale, but is it a lot on the astronomical scale, the solar scale? We're going to check it out. All right, so here we go. Per second. E equals mc squared. All right, so c is the speed of light. Go ahead and write it down. I think we already know this. 3 times 10 to the 8 meters per second. All right, 300 million meters per second. 5 light seconds between the sun and Earth. So, now, in his formula, you square that. That's the conversion factor. Right? And you'll read about this in chapter 15 and 16. I think this part's in 16. So c squared is 9 times 10 to the 16 meters squared per second squared. Right? So that's like a v squared. Remember, the kinetic energy formula was a 1/2, and then an m in kilograms, and then a v squared. The v squared in the kinetic energy formula is meters squared per second squared. All right? So we're looking good here. All right, now, here's the luminosity that we figured out. And how did we figure it out? We knew the solar constant, 1367, and we knew the size of the astronomical unit. We figured out 4 pi r squared and came up with 3.85 times 10 to the 26 watts. So that's the number of joules per second. And this right-hand side of the equation, that's the equals mc squared side. See this side over here, that's from observation and a little bit of geometry on the left. It's something we measure with telescopes, with spacecraft, bunches of different ways to measure the solar constant. Then over here, this is Einstein's theory. This is the mc squared part of the equation. All right? So let's break it down and let's convert both, or divide both sides by c squared. Okay, so we'll get delta m by itself. Here it is by itself. All right, and that's what we want to figure out. And here's c squared. Now, let's convert that denominator. So on a per second basis, this capital W here, put that, I should have changed it. I forgot to change it before lecture. That should be a capital J for joules. So this capital W here, per second, a watt is a joule per second. So we're going on a per second basis here. So change that to a J and c squared. And then down here now, kilogram meter per squared per second squared, that's a joule in metric units, basic metric units. And then here's the numerator, 3.85 times 10 to the 26. And then the denominator, 9 times 10 to the 16. And the
Unknown color.
good. The units on the bottom are meters squared per second squared. Now, look at those babies. They cancel. And so all you have left is kilograms. So go ahead and cancel meter squared per second squared here in the denominator. And cancel a meter squared per second squared up here in the numerator. But don't cancel the kilograms. That's good because we want a number of kilograms. All right. Now, what's 10 to the 26 divided by 10 to the 16? 10 to the 10, right? Right. 10 to the 10. And 3.85 divided by 9, so that's going to be about 2 point something. Or, I don't know, what is that? 0.428. Okay. Yeah, that's right. It's 1 over 2. So 1 over 2.7. So 0.428 times 10 to the 8. And that's what we found. Or that's the number that I cited for you. 0.428 times 10 to the 10 kilograms for every second of the sun's power. Through E equals mc squared, it takes this many kilograms. That's this number right here, 4.28 times 10 to the 9 kilograms per second that the sun loses and converts into luminosity through E equals mc squared. Right? Now, that's 4.28 billion kilograms. 4.28 million metric tons per second. But the sun itself, go ahead and make a note of this. The sun's mass is 2 times 10 to the 30 kilograms. It's got tons to burn. And this is no great shakes. So let's see how big the fraction goes per second. All right, so what we're going to do is take this 4.28 times 10 to the 9 kilograms and divide it by the total mass of the sun. Right? And that'll give us the rate. We know that it burns 4.28 times 10 to the 9 kilograms per second in the nuclear reactions. Gives us the luminosity, which we're able to figure out by terrestrial measurements of the solar constant. And we know from Kepler's third law, 2 times 10 to the 30 kilograms for the mass of the SUN. So this will give us the fraction of the sun's mass that goes every second. Right? So look at that. 10 to the 9 divided by 10 to the 30th. That's going to be 10 to the what? Yeah, it's 10 to the minus 21. So this is a totally small fraction of the sun's mass per second. 2.14 times 10 to the minus 21. Dude. The sun's got tons to burn, metric tons to burn. This is a very, very, it's not at 1%. It's not 1 per mil. It's not 1 part per billion. It's not 1 part per trillion. It's 2 parts per 10 to the 21. I don't even know what 10 to the 21 is. See, let's figure out what 10 to the 21 is. 1,000, million, billion, trillion, quadrillion, quintillion, sextillion. So this is 2 parts per 6 of the sun's mass. So it's very stable. Here's another way to look at it. The burn rate, 4.28 times 10 to the 9 kilograms per second. Let's convert that into a burn rate of how many kilograms per day, or excuse me, per year. Now, in 1 year, there are 31,536,000 seconds. So just go 365 times 24 times 60 times 60. And you get 31,536,000 seconds. All right, so now this number up here, multiply that by 31,536,000. And what do you get? You get this, 1.35 times 10 to the 17 kilograms per year. Now, how many years can that go on? Oh my goodness. Let's do it again. Total mass of the sun. We'll put that in the numerator. And then we'll burn it off at this rate per year. All right? So now this one is like saying, how long is it going to take me to go a certain distance at a certain speed? Okay, so if I tell you you have to go 100 miles at 40 miles an hour, you go 100 divided by 40, that's 2.5. Take you 2.5 hours. Same thing here. How much do you have to burn? 2 times 10 to the 30 kilograms. And what's the rate? 1.35 times 10 to the 17 kilograms per year. So how many years is that going to give you? All right, so here's the total mass of the sun. Here's how many kilograms it loses per year. So just take the quotient. And my wonderful students, ding, 1.5 times 10 to the 13 years. That is over 1,000 times longer, I should say, than the universe has been alive. We think of the universe as being on the order of 10 billion years old, we think, something like that. And this is way more than that. So here's your final side note before we dismiss. At this rate of burn, using E equals mc squared and knowing the solar constant, we know that the sun can burn at this luminosity for many, many billions of years to come. Now things will change. We think the sun, in a few billion years, things will change in the core. Because eventually the core is going to have more helium than it has hydrogen. And when that happens, it'll start to contract. And then you'll start letting off new reactions like carbon, nitrogen, and oxygen, which we'll talk about next week. Now, your reading assignment is going to be big. 15 and 16, I've got some additional reading assignments. And I'll put a little quiz in there, 4 or 5 reading questions. It'll be due on Tuesday. I hope to have it ready by lunchtime tomorrow. You're dismissed. All right, now I want to show you something here.
Thanks. Have a good weekend.
Yeah, see you later. Let me get my cursor here. Come on, cursor. There we go.